For what values of a and b is the following function continuous at every x? And so what we need is to have the function continuous everywhere. The best thing to do when you have a piecewise function like this is to use a number line to basically define the different parts of the function. At -1, the function changes from being the function y equals -1 to being the function y equals ax minus b minus 1. At 3, the function changes again and becomes y equals 9, or f equals 9. So our function has 3 different identities depending on which values of x you have. So we like it continuous everywhere. The function y equals -1 is continuous everywhere. Ax minus b minus, I'm sorry. It's very deceptive here. What we have to do is recognize that the ax minus b is where this thing ends at. There should be some kind of more separation, some sort of additional separation between the function and where the function is defined at. So that isn't ax minus b minus 1. That is just ax minus b. Okay. Great. But yeah, that's a line. And it's continuous everywhere, especially between -1 and 3. And then y equals 9 is continuous everywhere. So the question about being continuous everywhere then becomes a question about what's going on at these breakpoints. In order to have continuity, you need the limit from the left to be equal to the limit from the right, and then to be equal to the function value. And so let's go to the first thing, point A here, where the limit as x goes towards -1 from the left of this function is -1. The limit as x goes towards -1 from the right of this function is ax minus b, but we're evaluating it at -1. And so let me rewrite this and replace the function there. So it equals the limit as x goes to -1 from the left of the function -1, which is -1. Here it equals the limit as x goes towards -1 from the right of the function ax minus b, so we plug in a -1 for x. And what we get out is negative a minus b. The function value at -1 is -1 because of the equals to right here. And so these should all equal to each other. -1 should be equal to negative a minus b. Simplifying that, it's simply that a plus b is 1. Doesn't tell us directly what the value of a and b are, but it tells us that they should add to 1. Then we move to the second point here at 3. And it happens again. The limit as we approach 3 from the left-hand side of our function is the fact that we have to use, approach 3 from the left-hand side, we have to use the ax minus b function. And that's equal to plugging in a 3 for x. We get 3a minus b. The limit as x goes towards 3 from the right-hand side would be us using the function f to be 9. And that's just going to be 9. The function value at 3 is defined to be 9 because of the equal to there. So these have to equal each other. So 3a minus b has to be 9. Okay, so these two both have to be true for the function to be continuous everywhere, and we're looking at a system of equations. A plus b needs to be 1, and 3a minus b needs to be 9. Solve it however you like. I'm going to solve it using elimination, because I'm just going to add these two together. The b's cancel out, and you end up with 4a equals 10. Giving us the fact that a is 10/4 or 5/2. So we know what a is. Now let's go get b using the fact that they have to add to 1. If a plus b is supposed to be equal to 1, we subtract the 5/2 and we end up with negative 3/2. Okay, so we have the value of b. We have the value of a. We have the value of b. These are the values that would make this function continuous everywhere. But let's see it. Let's see the graph. If I plug in a being 5/2 and b being negative 5/2, let's take a look at the graph. We have the function constant -1. Then we have the line 5/2 x minus a negative 3/2 or plus 3/2. And then we have the function 9. And so the function is continuous everywhere, and we ensured that with those values of a and b, this center portion of the function will match up with the left and the right hand portion, and there will be no place where this function is discontinuous at. And that concludes the problem. Great.